Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. Many discoveries throughout our history have enabled us to better understand the universe around us. Even though we don't know everything, there are enormous sources of knowledge that have empowered us to draw far-reaching conclusions about our universe. We know what it's made up of in terms of matter, energy, radiation, and so on. We know that there are 400 billion within our galaxy and about 2 trillion galaxies are present throughout the visible universe. We know how the universe clumps and clusters together into galaxy groups, clusters and filaments, and how they're separated by vast cosmic voids. We know the scale of the cosmic distances defining these structures and how the universe is evolving over time. It's a remarkable story that all fits together beautifully in the framework of the Big Bang and general relativity theory. But along the way, experts have had to postulate the universe was not built for the human mind to understand. Up to now, all the stars, planets, and galaxies that can be seen today make up just 5% of the universe. The other 95% is made of stuff astronomers can't see, can't detect, or even comprehend. Worse, when we extrapolate back to the earliest stages of the universe and compare what we expect to observe, there are some big problems. Not long after the James Webb Space Telescope, or JWST, began beaming back from outer space its stunning images of planets and nebulae last year, astronomers, though dazzled, had to admit that something was amiss. 8 months later, based in part on what the telescope has revealed, it's beginning to look as if we may need to rethink key features of the origin and development of the universe. Join us today as we dig deep into how the James Webb Space Telescope has debunked all modern theories of the universe. The James Webb Space Telescope is a breathtakingly glorious feat of engineering. Built on the Hubble Space Telescope's discoveries, James Webb is a giant leap forward in our quest to understand the universe and our origins. It is a premier observatory with a large infrared telescope that has an approximately 6.5 meter primary mirror. The most cutting-edge engineering allowed Webb to examine every phase of cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, and planets, to the evolution of our own solar system. Launched at the end of 2021 as a joint project of NASA, the European Space Agency, and the Canadian Space Agency, the Webb, a tool with unmatched powers of observation, is on an exciting mission to look back in time at the first stars and galaxies, delivering and giving us a broader understanding of the origins of our universe. But the fact that the more curious we get about the great cosmic unknowns, the more unanswered questions our investigations of the universe will reveal. And the same is also true for James Webb. Indeed, one of Webb's first major findings was exciting in an uncomfortable sense. It discovered the existence of fully formed galaxies far earlier than should have been possible, according to the so-called Standard Model of cosmology. According to the Standard Model, which is the basis for essentially all research in the field, there is a fixed and precise sequence of events that followed the Big Bang. First, the force of gravity pulled together denser regions in the cooling cosmic gas, which grew to become stars and black holes. Then, the force of gravity pulled together the stars into galaxies. The Webb data, though, revealed that some very large galaxies formed really fast in too short a time, at least according to the Standard Model. This was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Unfortunately, it was not an isolated incident. There have been other recent occasions in which the evidence behind science's basic understanding of the universe has been found to be alarmingly inconsistent. Take the matter of how fast the universe is expanding. This is a fundamental fact in cosmological science, the so-called Hubble constant, yet scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as the sort that the Webb is providing. The other involves measurements of nearby stars in the modern universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better, but the problem has stubbornly persisted even as the data have gotten far more precise. And now, new data from the Webb have exacerbated the problem. This trend suggests a flaw in the model, not in the data. Two serious issues with the standard model of cosmology would be concerning enough, but the model has already been patched up numerous times over the past half-century to better conform with the best available data. Alterations that may well be necessary and correct, but which, in light of the problems we are now confronting, could strike a skeptic as a bit too convenient. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution, if you will, that would have implications far beyond the world of science. A potent mix of hard-won data and rare-field abstract mathematical physics, the standard model of cosmology is rightfully understood as a triumph of human ingenuity. It has its origins in the Edwin Hubble's discovery in the 1920s that the universe was expanding, the first piece of evidence for the Big Bang. Then in 1964, radio astronomers discovered the so-called cosmic microwave background, the fossil radiation reaching us from shortly after the universe began expanding. That finding told us that the early universe was a hot, dense soup of subatomic particles that has been continually cooling and becoming less dense ever since. Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. But along the way, to gain such a high degree of precision, astrophysicists have had to postulate the existence of components of the universe for which we have no direct evidence. The standard model today holds that normal matter, the stuff that makes up people and planets and everything else we can see, constitutes only about 4% of the universe. The rest is invisible stuff called dark matter and dark energy, roughly 28% and 68% respectively. Cosmic inflation is an example of yet another exotic adjustment made to the standard model. Devised in 1981 to resolve paradoxes arising from an older version of the Big Bang, the theory holds that the early universe expanded exponentially fast for a fraction of a second after the Big Bang. This theory solves certain problems but creates others. Notably, according to most versions of the theory, rather than there being one universe, ours is just one universe in a multi-universe, an infinite number of universes, the others of which may be forever unobservable to us, not just in practice, but also in principle. There's nothing inherently fishy about these features of the standard model. Scientists often discover good indirect evidence for things that we cannot see, such as hyperdense singularities inside a black hole. But in the wake of Webb's confounding data about galaxy formation and the worsening problem with the Hubble constant, you can't be blamed for starting to wonder if the model is out of joint. A familiar narrative about how science works is often trotted out at this point to assuage anxieties. It goes like this. Researchers think that they have a successful theory, but new data show it is flawed. Courageously rolling up their sleeves, the scientists go back to the blackboards and come up with new ideas that allow them to improve their theory by better matching the evidence. It's a story of both humility and triumph, and scientists love to tell it. And it may be what happens in this case too. Perhaps the solution to the problems the Webb is forcing us to confront will require only that cosmologists come up with a new dark something or other that will allow our picture of the universe to continue to match the best cosmological data. However, there is another possibility. We may be at the point where we need a radical departure from the standard model, one that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time itself. Cosmology is not like other sciences. It's not like studying mice in a maze or watching chemicals boil in a beaker in a lab. The universe is everything there is. There's only one, and we can't look at it from the outside. You can't put it in a box on a table and run controlled experiments on it. Because it is all-encompassing, cosmology forces scientists to tackle questions about the very environment in which science operates. The nature of time, the nature of space, the nature of law-like regularity, the role of the observers doing the observations. These rarefied issues don't come up in the most regular science, though one encounters similarly shadowy issues in the science of consciousness and in quantum physics. But working so close to the boundary between science and philosophy, cosmologists are continually haunted by the ghosts of basic assumptions hiding unseen in the tools we use, such as the assumption that scientific laws don't change over time. But that's precisely the sort of assumption we might have to start questioning in order to figure out what's wrong with the standard model. One possibility, raised by the physicist Lee Smolin and the philosopher Roberto Manganbeira Unger, is that the laws of physics can evolve and change over time. Different laws might even compete for effectiveness. An even more radical possibility, discussed by the physicist John Wheeler, is that every act of observation influences the future and even the past history of the universe. Dr. Wheeler, working to understand the paradoxes of quantum mechanics, conceived of the participatory universe, in which every act of observation was in some sense a new act of creation. It is not obvious, to say the least, how such revolutionary reconsiderations of our science might help us better understand the cosmological data that is flummoxing us. Part of the difficulty is that the data themselves are shaped by the theoretical assumptions of those who collect them. It would necessarily be a leap of faith to step back and rethink such fundamentals about our science. But a revolution may end up being the best path to progress. That has certainly been the case in the past, with scientific breakthroughs like Copernicus's heliocentrism, or Darwin's theory of evolution and Einstein's relativity. All three of those theories ended up having enormous cultural influence, threatening our sense of our special place in the cosmos, challenging our intuition that we were fundamentally different than other animals, upending our faith in common sense ideas about the flow of time. Any scientific revolution of the sort we're imagining would presumably have comparable reverberations in our understanding of ourselves. The philosopher Robert Crease has written that philosophy is what's required when doing more science may not answer a scientific question. It's not clear yet if that's what's needed to overcome the crisis in cosmology, but if more tweaks and adjustments don't do the trick, we may need not just a new story of the universe, but also a new way to tell stories about it. But noting that despite the universe itself may be finite or may be infinite, the part that's accessible to us is finite. Even with the expanding universe, even with all the galaxies and stars and planet and molecules and atoms and subatomic particles in it, there's only so much we can assess. And those limitations, the total number of particles and the total amount of energy available in the universe, means there's only a finite amount of information we can determine about our cosmos. The total amount of information accessible to us in the universe is finite, and hence, so is the amount of knowledge we can gain about it. There's a limit to the amount of energy we can access, the particles we can observe, and the measurements we can make. That doesn't mean we're done, or that we shouldn't strive to learn everything we absolutely can. Only we can push the frontiers of knowledge back as far as they can go. There's a whole lot left to learn, and a whole lot of science that is yet to be revealed. If we continue to look, maybe the present unknowns will likely fall in the near future. But what is knowable is finite, and this implies that there are necessarily some things we may never know. The universe may yet be infinite, but our knowledge of it will never be. Regardless, the James Webb Space Telescope's upcoming discoveries are still worth looking forward to. The JWST has completed successfully its first year of scientific operation in the vacuum of space from its location nearly 1.5 million kilometers away from Earth. In addition to taking the most detailed and breathtaking images ever of the iconic celestial objects, Webb completed its first deep field campaign, turned its infrared optics on Mars and Jupiter, obtained spectra directly from an exoplanet's atmosphere, blocked out the light of a star to reveal the debris disk orbiting it, detected its first exoplanet, and spotted some of the earliest galaxies in the universe, those that existed at the cosmic dawn. Now, as the James Webb Space Telescope enters its second year of capturing images of the depths of space, it has already revealed a treasure trove of beauty from around the universe, both near and far from home. A major focus of the Webb mission is the investigation of cosmic dawn, which began roughly 1 billion years after the Big Bang. Also known as the epoch of reionization, this period is so named because the first galaxies emerged during this time. This led to the reionization of the neutral hydrogen that permeated the intergalactic medium, or IgM, causing the universe to be transparent. This era is considered the final frontier of cosmological surveys because the extreme redshift and presence of neutral hydrogen make it impossible to study this period in visible light. The lack of transparency during this period led to it being nicknamed the Cosmic Dark Ages. The only way to detect light from this period is by observing the 21-centimeter transition line, a part of the ratio spectrum inaccessible to modern-day instruments, or the H-alpha emission line, which is visible in the mid-infrared spectrum. According to a recent study, an international team led by the Capitan Astronomical Institute, or CAI, resolved the H-alpha emission line using data from the Webb's MIRI instrument, thus providing the first confirmed detection of galaxies at cosmic dawn. During Cycle 2, astronomers intend to push the boundaries even farther. For starters, Pi Carl Glazebrook of the Swinburne University of Technology and an international team were allotted 615 hours to conduct a JWST-wide Area 3D parallel survey. This will consist of pure parallel observations using JWST's near-infrared imager and slitless spectrograph, or NIRISS, of an area covering 1,000 square arc-minutes. The resulting survey, they claim, will provide spectra and redshift measurements for 60,000 galaxies from cosmic noon to cosmic dawn, circa 10 to 11 billion to 13 billion years ago, from the first stars and galaxies to the birth of the second generation of stars, or population 2 stars. Such a large area redshift survey will allow us to measure 3D clustering in the cosmic growth era, revealing the detailed connection between dark matter halos and assembling baryons. It will also provide a benchmark set of stellar mass functions for complete spectroscopic type defined samples, address the origin of galactic quenching, provide 2D abundance and age measurements of galaxies measuring galactic buildup, and provide a census of rare Z greater than 11 bright galaxies and other rare objects at all redshifts. The size of the survey will also enable data-driven discovery with advanced machine learning approaches, revealing novelties and surprises in the early universe, Carl Glazebrook and his research team said. In addition, Pi Hakim Atek of the Institute of Astrophysics at Paris and his colleagues proposed the gravitational lensing and near-cam imaging to probe the early galaxy formation and sources of reionization or glimpse they call it, observation campaign. By taking ultra-deep images with Webb's near-infrared camera, the NIRCam, ATEC and his team will observe low-mass galaxies a few 100 million years after the Big Bang. During their 148 hours of observation, they hope to investigate the mechanisms governing galaxy formation, such as gas accretion, star formation, and the subsequent feedback inhibiting further star formation. This, they claim, will achieve three main goals. We propose, they say, to combine the power of strong gravitational lensing with ultra-deep NIRCam imaging to achieve these three main goals. Number one, to measure the prevalence of faint galaxies at a Z greater than 6 to establish, for the first time, key observational benchmarks for galaxy formation models, which have never been confronted to this uncharted territory. Secondly, strongly constrain the contribution of the faintest galaxies towards cosmic reionization. And thirdly, probe the typical galaxy population during the Dark Ages that remains out of reach of current programs. Professor Daniel Einstein of Harvard University and an international team were awarded 137.1 hours for their proposal, unveiling the redshift frontier with JWST. This will consist of a deep 6-filter medium-band imaging survey with a NIRCam to identify galaxies at the redshift frontier Z equals greater than 15. The properties of these very early galaxies will test and inform theories of galaxy formation and allow astronomers to make discoveries about the physics of the early universe. This includes theories about the possible presence of early dark energy to explain the discrepancy between measurements of cosmic expansion, aka the Hubble tension. They also plan to conduct this survey parallel to a deep multi-object spectroscopy campaign conducted with NIRSpec of galaxy candidates in and around the Hubble Ultra Deep Field, or HUDF. These spectra will provide detailed information about individual high redshift galaxies, not just stacks or averages, allowing us to study the chemical enrichment, stellar populations, star formation histories, and nuclear black holes in the first billion years of the universe, they state. In addition, one of the most anticipated aspects of the Webb mission is how it will assist with the transition currently taking place in exoplanet science. Whereas astronomers were largely focused on the discovery process in the past, improved instruments, methods, and analytics are shifting the focus towards characterization. To date, the vast majority of exoplanets have been detected by indirect means, which meant that constraints on their habitability had to be inferred based on their parent star, the distance at which they orbited, and their respective masses. But thanks to Webb's superior infrared optics and sensitivity, astronomers look forward to being able to directly image exoplanets and obtain spectra from their atmospheres. In particular, they hope to direct Webb's mirrors toward nearby M-type or red dwarf stars and their rocky planets, many of which have been confirmed in recent years. In addition to being the most common stars in the universe, accounting for about 75 to 80%, red dwarfs are also likely to support rocky planets within their habitable zones, or HZs. However, these planets are likely to be tidally locked with their suns, and red dwarfs are prone to flare activity, which raises questions about their long-term ability to retain atmospheres. To address this mystery, Dr. Shubham Kanodia of the Carnegie Institution of Washington and his team were awarded 132.39 hours for their program titled Red Dwarfs and the Seven Giants. This sweetly named study will characterize the atmospheres of giant rocky planets around M-type stars to address one of the JWST's primary science goals: how atmospheric composition can affect a planet's formation and evolutionary history. This will consist of Kanodia and his team using Webb's near-infrared spectrometer, or NIRSpec, to observe short-period Jupiter-sized planets around red dwarfs, which pose challenges to current theories about planet formation and represent an extreme regime that is poorly understood. By comparing the atmospheres of 7 M-dwarf short-period Jupiters to the gas giants that orbit our Sun, they hope to characterize their atmospheric composition and metallicity and compare them to gas giants that orbit more massive yellow-type or F-type Sun-like or G-type and orange dwarf K-type stars. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. And as always, thanks for watching, and we'll see you next time.
December 25 will bring many reasons to celebrate. It's an annual festival commemorating the birth of Jesus Christ. But in astronomy, that day is also the 2-year anniversary of the launching of NASA's James Webb Space Telescope, humanity's greatest space-based observatory of all time. Launched on Christmas Day 2021, James Webb has been our cosmic workhorse, revealing the universe in a whole new light, with unprecedented resolution and wavelength coverage to view the cosmos. And now, to celebrate its 2nd birthday, James Webb has just left astronomers feeling festive recently as it allowed them to image a distant, colorful cluster of galaxies they have dubbed the Christmas Tree Galaxy Cluster. In this cluster, the James Webb Space Telescope discovered flickering Christmas lights in the form of 14 new transient objects, celestial objects that brighten dramatically before dating. The winter wonderland is officially called Maxil 416 and is located about 4.3 billion light-years from Earth. As Haojing Yan, an associate professor in the University of Missouri Department of Physics and Astronomy, said in a statement, "We're calling Max 0416 the Christmas Tree Galaxy Cluster, both because it's so colorful and because of the flickering lights we find within it. Transients are objects in space, like individual stars, that appear to suddenly brighten by orders of magnitudes and then fade away. These transient objects appear bright for only a short period of time and then are gone. It's like we're peering through a shifting magnifying glass." Spotting so many transients in this galaxy was achieved by teaming the JWST up with the Hubble Space Telescope. The sheer number of transients spotted in one go, thanks to the duo, implies there are a lot more yet to be found within the Christmas Tree Galaxy Cluster. It's almost like the Christmas gift for astronomers that'll keep on giving. The light from the Christmas Tree Galaxy Cluster began its journey across the cosmos when the solar system, now 4.6 billion years old, was newly formed and just around 300 million years old. This would ordinarily make it too faint for even the Webb telescope to see in detail, but a little trick first acknowledged by Albert Einstein made observing this cosmic Christmas a little easier. In his 1915 theory of general relativity, which concerns the nature of gravity, Einstein said objects of great mass must warp the very fabric of space and time, united as a single entity called space-time, giving rise to a curvature we experience as gravity. And when anything, including light, passes these curved regions of space, those things' paths get curved. The closer to the body of mass a thing is, the more extreme the curvature it experiences. As a result, when an object passes between Earth and a distant light source, the light from that background object takes a varied amount of time to reach us, as its path isn't following a straight line due to the curvature created by the passing object. This can ultimately cause that background object to appear amplified from our vantage point. The concept is called gravitational lensing, as the intervening object acts as a natural, cosmic magnifying glass. James Webb has been tapping into this phenomenon with great success to see some of the universe's earliest galaxies, and its view of the Christmas Tree Galaxy Cluster is its latest example. Look at this picture. We can see so many transients in certain regions of this area because of a phenomenon known as gravitational lensing, which is magnifying galaxies behind this cluster. Right now, we have this rare chance that nature has given us to get a detailed view of individual stars that are located very far away. While we are currently only able to see the brightest ones, if we do this long enough and frequently enough, we will be able to determine how many bright stars there are and how massive they are. The transients were found by Yan and the team as they were looking at 4 sets of images captured by James Webb over around 4 months as part of the James Webb Space Telescope's Pearls GTO 1176 program. The team has identified 2 objects in the images as supernova explosions that happen as stars reach the end of their lifespans. They are thrilled by this result, as they now use those supernovas to study the galaxies in which they are happening. Moreover, the astronomers also found something else extraordinary in the Christmas Tree Galaxy Cluster, a monster star in a galaxy, seen as it was when the universe was just 3 billion years old. They have named the star Mothra after the monstrous moth kaiju from Japanese cinema. The galaxy in which Mothra lurks was lensed to around 4,000 times its original brightness. The object lensing this galaxy is currently unknown, but Yan and the team estimate it has a mass of between 10,000 and 1 million times that of the Sun. As José Diego, research lead author and a scientist at the Instituto de Física de Cantabria scientist, said in a separate statement, the most likely explanation is a globular star cluster that's too faint for the James Webb Space Telescope to see directly. But we don't know the true nature of this additional lens yet. What is extra interesting about Mothra's galaxy is the fact it was also visible and lensed in Hubble Space Telescope images taken 9 years ago. Normally, a lensing object and a background galaxy would move out of alignment over such a period. But Mothra's home galaxy and the object lensing, it seemed to have stuck together. In the future, Yan and the team hope to both figure out the nature of this lensing object and uncover some of its characteristics. As Yan concluded, we'll be able to understand the detailed structure of the magnifying glass and how it relates to dark matter distribution. This is a completely new view of the universe that's been opened by James Webb. One of 2 papers detailing the observation of the Christmas Tree Galaxy Cluster was published in November in the journal Astronomy and Astrophysics, while the other has been accepted for publication in the Astrophysical Journal with a preprint available on the research repository Archive. Notably, this James Webb shot isn't the only Christmas-themed image in space this year. Just a few weeks ago, an image of Cassiopeia A, the remains of a star that exploded 340 years ago, was also unveiled by the First Lady, Jill Biden, as part of a new White House Advent calendar. These images and others follow a long tradition of astronomers and other stargazers connecting the season of light with cosmic phenomena occurring light years from Earth. But there is genuine scientific wonder involved in some of these festive observations. Unlike the Christmas Tree Galaxy Cluster, Cassiopeia A is a lot closer to home. Scientists have long studied the violent stellar explosion and others like it to figure out their role in cosmic evolution. They help galaxies grow. Danny Milosavljevic, an astrophysicist at Purdue University who studies Cassiopeia A, wrote in an email, "Supernova remnants also create the elements needed to sustain life, like the oxygen we breathe, the iron in our blood, the calcium in our bones. At 11,000 light-years from Earth, Cassiopeia A has been observed by a variety of space telescopes in visible, X-ray, and infrared wavelengths. But the Webb's new infrared vision affords a better view. In April, NASA released an image of the supernova remnant using the telescope's mid-infrared instrument. The latest snapshot makes use of the Webb's near-infrared camera, which captured gas, dust, and molecules radiating at warmer temperatures. The pink and orange structures, enveloped in smoky material against a glittering backdrop of stars, resemble an ornament hanging from a tree branch. As Dr. Milosavljevic said, 2 years ago, Webb launched flawlessly on Christmas morning. At the time, I thought it was the best Christmas gift ever. But the telescope is the gift that keeps giving. What's interesting is James Webb isn't the only observatory sending us Christmas gifts. A distant star-forming nebula, looks like a turkey fleeing a cosmic Christmas dinner, has just been captured in a new image by the European Southern Observatory's Very Large Telescope in Chile. The festive photo features the star hatching clouds of gas and dust that comprise the nebula IC2944, located around 6,500 light-years from Earth. IC2944 has a distinctly fowl-like appearance, so astronomers have nicknamed it the Running Chicken Nebula. In the stunning new 1.5 billion pixel Very Large Telescope image, the wispy gas and dust tendrils of the nebula glow in red, pink, and orange, punctuated by bright blue stars like lights shining on a Christmas tree. The Running Chicken Nebula is about 71 light-years wide and lies toward the constellation of Centaurus. It contains several separate regions, all of which are present in the new image, which covers a patch of the sky as wide as 25 full moons. The brightest region, which appears as the rear of this cosmic fowl, is known as IC2948. This area is stuffed with bright gas and dust plumage and punctuated with bright blue light from hot young stars. These stars, which are spread through the rest of the nebula as well, are carving this cosmic chicken by emitting vast amounts of ultraviolet radiation, which disperses gas and dust and thus helps to curtail further star formation. But some regions of the running chicken, known, no joke, as Bach globules, are resisting this high-energy radiation and can be seen as dark, dense pockets of gas and dust sprinkled around the nebula. Further up, the celestial chicken is a bright, vertical, pillar-like structure called IC2944, which appears almost like a chicken wing in the process of flapping. Atop IC2944 is the twinkling star Lambda Centauri, which is closer to Earth than the Running Chicken Nebula at just 470 light-years away. The star is so bright that it's visible from Earth with the naked eye. In the upper right of the image, two emission nebulas, regions of superhot ionized gas, called GUM39 and GUM40, make up the head of the running chicken. A further emission nebula, GUM41, can be seen to the lower right of the image, forming the foot of the cosmic chicken. Completing the new image is a sprinkling of white and blue stars that resemble falling flakes of snow, each one as unique, individual, and complex as an actual snowflake. Meanwhile, elsewhere in space, to celebrate the festive season, the Hubble telescope also has just gifted us a dazzling starry snow globe which resembles something of a wonderland of Christmas lights. The image's subject is the billion star containing UGC 8091, an irregular dwarf galaxy located within the constellation Virgo, some 7 million light-years from Earth. To create the luminous, chromatic effect we see, scientists compiled data captured by the Hubble Space Telescope's Wide Field Camera 3, an advanced camera for surveys between 2006 and 2021. They ran the data through 12 filters that sampled both broad and narrow wavelengths that covered mid-ultraviolet to visible red light. The red patches are thought to be interstellar hydrogen molecules, while the sparkles within are older stars. In the very background are other distant galaxies so far away, they almost appear to be single stars. Truthfully, we think that seeing shapes in space telescope images, Christmas, related or otherwise, is just like seeing shapes in clouds. It's all open to artistic interpretation. But there's no denying that the images are beautiful, no matter what they resemble. In short, even the cosmos is wishing you a happy holidays. Now, on the threshold of the new year, let's take a quick look at the most astonishing, jaw-dropping James Webb moments from 2023. 1. Our most distant black hole ever. It was only last month, while combining Chandra X-ray data with James Webb's deep infrared views of galaxy cluster Able 2744, that scientists revealed a tiny, distant early galaxy with only around 10 to 100 million solar masses worth of material in it. But that was incredibly X-ray luminous, indicating an active black hole of around 9 million solar masses. Not only is this the most distant black hole ever discovered, it's also our first example of such an extreme mass ratio, where the central black hole is right around as massive as all the stars in the host galaxy combined. Our understanding of black hole galaxy formation and coevolution will never be the same. 2. New insight of the Crab Nebula. In the year 1054, a supernova went off in the Milky Way galaxy, so brilliant and enduring it was visible from Earth for a long period of time. Now, nearly 1,000 years later, we can look in that same region of sky and find the Crab Nebula, a supernova remnant more than 10 light-years across, with a young, energetic, spinning neutron star at its core, the Crab pulsar. Whereas Hubble's visible light views highlight various elements and knots of gas that reflect light, James Webb's infrared views showcase the presence of dust, accelerated electrons, and even the carved-out features by the central pulsar's winds and magnetism. The question of the mass mystery, or of where all the supposedly missing material that would have been needed for the progenitor star to explode, may yet find its solution in the still being analyzed Webb data. 3. James Webb's deepest ever view. The James Webb Space Telescope, Advanced Deep Extragalactic Survey, or JD's, collaboration has released a fully zoomable, explorable view of their field, with various NIR cam filters and NIR spectra capable of being overlaid atop an enormous set of the objects imaged. Although this represents a relatively narrow field of view in the sky, it contains the most distant galaxy ever discovered so far, as well as a slew of candidate objects that may yet prove to be even farther away. It showcases the incredible reach and variety of what's possible with James Webb. 4. A sneak peek inside the Orion Nebula. Under James Webb's sharp eyes, there are an enormous number of brilliant, glittering new stars still in the process of forming. Some of them, shown here, are Herbig-Haro objects, massive young stars that are highlighted by stellar outflows. In other cases, there are protostars, still in the process of formation, young singlet and binary stars that have already finished forming, and nebulous regions that even James Webb cannot penetrate. Lastly, there were some surprises. Jupiter mass objects that are members of no stellar system, including a surprisingly large fraction of them that are binary objects. The images are as beautiful as the science is profound. 5. The most distant gravitational lens ever. At the center of this image, a massive compact galaxy is found, located about 17 billion light-years away within this expanding universe. The ring around it, with 2 red spots, is actually a single, more distant galaxy that's located along the same line of sight as the closer galaxy, but gravity has distorted it into a ring, an example of gravitational lensing. While more distant background lenses have been spotted, this represents the most distant foreground lens, the object actually doing the lensing ever discovered. 6. The most massive galaxy cluster for its time. Although galaxy clusters are found all across the universe, they're expected to grow larger and larger in mass over cosmic time. For the time at which it was discovered in the universe, the El Gordo galaxy cluster, imaged here by James Webb, is the most massive one known, with over 2 quadrillion solar masses of material inside it, despite its light coming from more than 5 billion years ago. Within this cluster, marked A and B, are the gravitationally lensed galaxies known as La Flaca. In reality, both of these lensed galaxies are completely normal. Their light is stretched into these unusual shapes by the foreground gravity of the galaxy cluster in front of them. 7. the most distant red supergiant star ever. Located in the same field as El Gordo, and hence in the same field as the Fishhook and the La Flaca lensed galaxies, is a single red supergiant star known as Quiller, the most distant red supergiant ever discovered. Although the previously discovered star Earendel, also imaged by James Webb but discovered first by Hubble, is even farther, this shows that finding individual stars in the early universe isn't a one-off proposition, but rather that the combination of Webb's incredible capabilities plus the enhancement of gravitational lensing can reveal individual stars farther back in cosmic time than via any other method. 8. Triply lensed supernova Harpy discovered. Sometimes very distant galaxies have their light stretched out into multiple images by the effects of gravitational lensing. When we're very lucky, a transient event, such as a supernova, will occur in that lensed galaxy, allowing humanity to observe the supernova event on replay in each of the multiple images. The reason this provides such hope, or arak in this case, is because the quest to measure the expansion rate of the universe today, also known as H0 or the Hubble constant, gives two different answers dependent on which set of methods are used. The discovery of supernova H0PE provides a potential way to resolve this conundrum over the expanding universe, and perhaps future observations of multiply-lensed supernovae, which James Webb should be outstanding at finding, will be just what we need to resolve the so-called Hubble tension. 9. Dusty secrets within spiral galaxies. Most of the images we see of spiral galaxies are taken in visible light, where the stars shine brightly but where neutral matter, particularly dust grains, appear dark, blocking that light. Not so with Webb's MIRI instrument, which highlights and illuminates the dust inside these galaxies, showing the locations of future and current new star formation. In this view of galaxy NGC7496, not only are the dust lanes prominently revealed, along with the pinkish-white regions showcasing regions where new stars are already forming, but the center of the galaxy exhibits brilliant diffraction spikes, evidence for an actively feeding supermassive black hole at the galaxy's center. 10. The Ring Nebula. Viewed with both the NIR-CAM and MIRI instruments independently, this nebula is among the most famous planetary nebulae known. What's left behind when a dying sun-like star blows off its outer layers in its death throes, while its core contracts down to form a white dwarf. You can find, in both views, intricate details of the inner filaments, which are actively being evaporated away by radiation, as well as roughly 10 concentric arcs outside of the main ring feature that are hydrocarbon-rich in the MIRI image. No other observatory has ever revealed this level of detail inside the Ring Nebula. 11. The stunning view of Saturn's rings. Whereas Saturn itself is a relatively cool planet with a cloud and haze-rich atmosphere separated into bands by latitude, it's mostly very faint in infrared light. However, its rings are 99.9% composed of water ice, which is even more reflective in infrared light than in visible light, leading to this unique and stunning view of Saturn's rings. In this image from James Webb, the A, B, C, and F rings are all visible, as are the Cassini division and the NT gap. Saturn was the final gas giant planet in our solar system, imaged by James Webb, completing our solar system's family portrait. 12. Uranus, new and improved. Although James Webb caught its first view of Uranus in February of 2023, the data it acquired on September 4, 2023 shows a far more spectacular view. 9 of its 13 inner moons, plus all 5 of its main large moons, are all revealed, as are at least 5 of its rings, along with several features on the planet itself. A dense polar cap that fades away toward equatorial latitudes, punctuated by a dark band and with Uranian storms ranging closer to the equator. As Uranus approaches its solstice for the first time since 1986, these Webb views teach us information that no other observatory can reveal. 13. a cosmic sparkler. Although this shows a portion of the very first science image released by James Webb, it wasn't until January of 2023 that this remarkable feature, known as the sparkler galaxy, was discovered in Webb data. In the yellow boxes shown above are 3 images of the same distant galaxy, lensed, stretched, and magnified by the gravity of foreground cluster SMACS 0723. The sparkles that are most easily visible in the largest central image are actually globular clusters that are brightly undergoing new episodes of star formation. When James Webb examined these clusters in detail, it found that they already had older populations of stars inside, shedding new light on how second bursts of star formation can occur inside globular clusters, a feature that only a fraction of all known globular clusters possess. 14. An intermediate belt surprise. We've often looked at our solar system as the prototype for what we expect to find elsewhere in the universe. While planets can exist both close to and far from a star, we expect there to be a series of frost lines, with the innermost one corresponding to an asteroid belt and the outermost one corresponding to a Kuiper belt. Yet, when James Webb examined the young stellar system Fomalhaut, it found something our solar system doesn't possess: an intermediate belt, found exterior to the inner disk where the asteroid belt should be, but interior to the Kuiper belt analog. Is this feature typical of stellar systems, meaning we're the outlier, or is it unusual, meaning it's the outlier? More data is needed, but this is a puzzle we didn't even know would need to be solved prior to 2023. 15. The most distant galaxy cluster ever. Earlier in 2023, scientists spectroscopically analyzed a series of distant, very red, faint galaxies found in the field of view behind Pandora's cluster, Abell 2744. They found that at least 7 of these galaxies are at precisely the same redshift, indicating the presence of a proto-galaxy cluster, the earliest one ever found at just 650 million years after the Big Bang. While Hubble had found the earliest proto-galaxy cluster previously known at 800 million years after the Big Bang, and the Sierras collaboration found one just 1.2 billion years after the Big Bang, this cluster, with a mouthful of a name of A2744Z7P90D, was discovered by the Glass collaboration, showcasing the importance of viewing many different areas of the sky in the quest for the most distant classes of objects of all. These 15 images represent just a tiny fraction of the views and science that have come out of James Webb, and the best part is we likely have another 20 years of excellent Webb science to look forward to. The great cosmic story and our understanding of it is in many ways only beginning to be unfolded. So buckle up, the cosmos is waiting. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Most of us are familiar with the standard narrative of how the universe began. There was an infinitely dense point of an infinite temperature with no size called a singularity. This singularity exploded, creating all the space, energy, and matter that we consider to be our universe in an event called the Big Bang. Between 10 to the power of -36 seconds and 10 to the power of -32 seconds, space expanded exponentially, growing much, much larger in size. After this period, space continued to expand, but at a much slower rate, and eventually, we see the universe that we observe today. This is the inflationary Big Bang theory, the most popular and broadly accepted theory of how the universe began. But for a few physicists, the premier theory doesn't paint an accurate picture of the evolution of our universe. Rather, they say that the universe existed before that point, stretching forever into the past as well as the future. While the universe is expanding today, it was contracting in the time before the Big Bang. In this picture, the Big Bang isn't so much a bang, but a bounce, a moment when a shrinking universe reversed course and began to grow. And according to their theory, the universe could bounce again. Today's expansion could be followed by collapse in the far future, followed by another bounce. Some physicists have suggested this bouncing could be infinite. This, of course, is counter to the way most cosmologists see it, where everything started with the Big Bang. But what is noteworthy here is this is not the only theory that dares to challenge the pinnacle theory of cosmology. Renowned physicist Brian Cox also challenges the Big Bang theory, asserting that something cannot emerge from nothing. Adding a bit of tension, the James Webb telescope has made a bunch of unexpected discoveries that contradict the notion that the Big Bang marked the beginning of the universe. All of these raise a question. If the Big Bang wasn't the beginning of the cosmos, then what was it? Could the universe start with a bounce, or something else entirely? Join us as we dig deep into one of the thorniest in physics. The idea that the universe had a beginning, or a day without a yesterday, as it was originally known, goes all the way back to Georges Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that describes our early universe. Although many laypersons and even a minority of professionals still cling to the idea that the Big Bang means the very beginning of it all, that definition is out of date. The Big Bang now is not the birth of time and space. We know that today, in 2023. In fact, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures. There's a cutoff. Instead, our universe is best described by an inflationary period that occurred prior to the Big Bang. And the Big Bang is the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. There were no particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time, by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new, small-scale fluctuations are created atop them. This superposition of fluctuations, of small scales atop intermediate scales, atop large scales, atop superhorizon scales, is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on. But inflation will come to an end randomly, and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang, before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a human-sized hamster ball, but perhaps much larger, the energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of negative 33 seconds or so, a brief amount of time, but nonetheless one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise, from just a few degrees above absolute zero to perhaps 20 Kelvin or so, over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. it doesn't matter under these conditions. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats, and the hot Big Bang starts, more distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate there drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, that distance doubles yet again and again and again. The process is relentless. But once the Big Bang begins, all of that changes, as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation, and expand more slowly than the still inflating regions do, leaving you, in the inflating region, as a typical region within space-time dominating its volume. These regions, where hot Big Bangs occur, will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes, where separate hot Big Bangs occur, will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and the only departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. But that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today, as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions. Even at that, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem it has sometimes been called a crisis for cosmology. Third, the 2 hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense, since we believe that the universe should have started out uniform, on average. And last, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby Cepheid stars. Taken together, these anomalies mean we're missing something fundamental in our understanding of the universe. The answer may lie in loop quantum cosmology. Loop quantum cosmology arises from loop quantum gravity. In loop quantum gravity, gravity itself is made of particles called quanta. These quanta come together to form the fabric of space and time. In this model of the universe, there is a smallest size of space itself, the Planck scale, or 10 to the power of negative 35 meters. Nothing, not even space itself, can be smaller than this. This means that the Big Bang couldn't exist in a universe with loop quantum cosmology. The universe could never get down to an infinitely small, infinitely dense point. Close to the Big Bang, when the universe was very small, really weird things happen mathematically. Infinities start to arise and threaten to tear the fabric of space-time itself. It's at these locations where loop quantum gravity can come in to provide corrections to the physics we already know. As Dr. Abhay Ashtekar at Penn State University, who led a study showing that the universe started in a bounce rather than a bang, said, "At such places, one has to use quantum geometry underlying loop quantum gravity. The quantum-corrected equations predict that there is an effective repulsive force. This means in these regions, when the universe is very small, the repulsion would result in a bounce. If our universe originated in a bounce, that means there was another universe before us. That universe went through its life, perhaps expanding and eventually contracting once again. As all of the matter and space-time of this universe came together, it ended in a spectacular fireball. Then, in a giant bounce, our universe was born, like a phoenix rising from the ashes of the old universe. This isn't entirely a new idea. Physicists have tossed around the idea of the Big Bounce for several decades. Even farther back, cyclic time is present in Hindu cosmology. If loop quantum cosmology is the correct model of the universe, in its infancy, the universe would have had very high curvature. To visualize this, think of a globe has positive curvature, a sheet of paper has flat curvature, and a saddle has negative curvature. If the universe was strongly curved when it was young, evidence of this would show up in the cosmic microwave background. When you look at the cosmic microwave background, you realize that it is not uniform. It's close, but there are small differences in temperature from one point in the sky to another. If you plot these temperature differences as a function of scale, you get one of the most powerful tools of cosmology, the angular power spectrum. Evidence of the curvature of the early universe would show up in the angular power spectrum of the cosmic microwave background. Some of these effects would show up at extremely large scales, larger than the size of the universe. This is a problem, obviously. We won't be able to observe it. However, luckily for us, these large scales interact with smaller scales, providing us with indirect evidence of this early phase of the universe. One of the effects of these interactions is to create the hemispherical anisotropy, says Ashtekar. In our current understanding of the universe, the probability that the two hemispheres of the sky would be different is very small. But with loop quantum cosmology corrections, the probability is enhanced and the observed anisotropy is no longer anomalous. That means that loop quantum cosmology would provide an explanation for anomaly number 3, why the hemispheres in the sky have different average temperatures. In addition, using the model of the universe that loop quantum cosmology provides solves the first 2 anomalies that we have seen in the cosmic microwave background: strange behavior at large scales and lensing. According to Dr. V. Srinath of the National Institute of Technology, Karnataka, this possibility that cosmic microwave background anomalies are not just statistical flukes, but rather effects due to quantum gravity happening very early in the universe is very exciting. But how sure are we that the universe originated in a big bounce? Except that, with all major claims, extraordinary evidence is needed. The idea that the universe originated in the Big Bounce has been suggested several times. We'll have to see if this one sticks. Another problem: our observations are limited, and it may just be that we are observing a part of the universe that is unusual. That's a problem called cosmic variance. As Dr. Donghui Zhong, a co-author of the paper and professor at Penn State University, said, "It is hard to confirm with 100% confidence because of the cosmic variance. But what is intriguing is that including this new possibilities can resolve two issues at the same time: the large-scale power suppression and small-scale lensing amplitude. Ruling out signs of an loop quantum cosmology-driven cosmic bounce in Planck, data means the cosmic microwave background anomalies remain unexplained. But an even larger cosmic issue lingers. Did the universe have a beginning at all? As far as advocates of the Big Bang are concerned, it did. But that leaves us with the inscrutable singularity that started everything off. Alternatively, according to theories of so-called cyclic cosmologies, the universe is immortal and is going through endless bounces. Although a bouncing universe may experience one or more cycles, a truly cyclic universe has no beginning and no end. It consists of a series of bounces that go back for an infinite number of cycles and will continue for an infinite number more. And because such a universe doesn't have a beginning, there's no Big Bang and no singularity. But physicist William Kinney of the University at Buffalo points out that there is a critical flaw lurks in the idea of an eternally cycling universe. That flaw is entropy, which builds up as a universe bounces. Often thought of as the amount of disorder in a system, entropy is related to the system's amount of useful energy. The higher the entropy, the less energy available. If the universe increases in entropy and disorder with each bounce, the amount of usable energy available decreases each time. In that case, the cosmos would have had larger amounts of useful energy in earlier epochs. If you extrapolate back far enough, that implies a Big Bang, like beginning with an infinitely small amount of entropy, even for a universe that subsequently goes through cyclic bounces. If you're wondering how this scenario doesn't violate the law of conservation of energy, we're talking about available energy. Although the total amount of energy in the cosmos remains static, the amount that can do useful work decreases with increasing entropy. New cyclic models get around the problem by requiring that the universe expands by a lot with each cycle. The expansion allows the universe to smooth out, dissipating the entropy before collapsing again. Although this explanation solves the entropy problem, Kinney and his University at Buffalo co-author Nina Stein calculated in their recent paper that the solution itself ensures that the universe is not immortal. As Kinney says, "I feel like we've demonstrated something fundamental about the universe, which is that it probably had a beginning. That implies a Big Bang occurred at some point, even if that event happened many bouncing universes ago, which in turn suggests that it took a singularity to get everything going in the first place." Kinney's paper is the latest in the debate over cyclic universes, but proponents of a universe without beginning or end have yet to respond in the scientific literature. Two leading proponents of a cyclic universe, astrophysicists Paul Steinhardt of Princeton University and Anna Ijas of New York University, declined to comment for this article. If the history of the debate is any indication, though, we may soon hear of a workaround to counter Kinney's analysis. Some physicists say the Planck data only rule out a bounce under a loop quantum cosmology model that can explain away the cosmic microwave background, anomalies through the bispectrum, not other loop quantum cosmology bounce models that address anomalies using different mechanisms. Cosmologist Nelson Pinto Neto of the Brazilian Center for Physics Research, who has studied bouncing and other cyclic models, agrees that loop quantum cosmology bounces that account for the cosmic microwave background. Anomalies are likely off the table now, but he's more sanguine on the question of a cyclic universe. According to Nelson, existence is a fact. We are all here and now. Non-existence is an abstraction of the human mind. This is the reason he thinks that a cyclic universe, which has always existed, is simpler than one that has been created. However, as a scientist, he must be open to both possibilities. While the origin of our universe is still a mystery, there was a contentious argument about how the universe would end. The details of this narrative depend on the kinds of stuff the universe contains. The cosmic recipe determines how the universe changes in time and what kind of future it will have. There are essentially two possibilities. In one, the universe will keep on expanding forever, because stars have finite lives. At some point far in the distant future, they will be extinct. Stellar corpses will dot the universe, from slowly smoldering white dwarfs to black holes of different sizes. But drama can be added here, depending on what kinds of matter the universe contains. If the current recipe remains viable, there are three main ingredients: dark matter, dark energy, and the stuff we are made of, the normal matter of protons and electrons. Assuming normal matter and dark matter are stable in the long term, dark energy controls the future of the universe. If dark energy, this ether-like substance of unknown composition, is a constant, that is, if its density does not change and it maintains a fixed volume irrespective of cosmic expansion, then the universe's expansion will keep on accelerating. In extreme scenarios, it may have so much negative pressure that it will rip everything apart, decomposing matter back into its basic ingredients. Instead of from dust to dust, the cosmic epitaph would be from particles to particles. But it is also possible that dark energy is not like that, and that its negative pressure will fade with time, no longer fueling the universe's rapid expansion. Acceleration will lose pace, and the universe will retain the faded stars and their corpses, all resting far from each other, the ultimate cosmic loneliness. The sad part is that in a cosmos without room for entropy to grow, matter cannot reorganize into anything interesting. This is the cold cosmic death scenario. If nothing changes, time itself loses its function and reaches an end. Another possibility is that the expansion will slow down. If there is enough matter out there, it may revert itself and push the universe from expansion into contraction. Eventually, matter that was dispersed for billions of years will compact back into a small volume, heat up, reach crushing densities and, well, it depends. It may go into a big crunch, the inverse of the Big Bang, or it may reach a point of maximum contraction and then bounce outward into a new phase of expansion. This is the bounce universe model, where the universe trades periods of expansion and contraction, never quite reaching the point of infinite density or initial singularity. Time keeps on ticking, although each cycle needs new clocks. Every end of time marks the beginning of a new time, a new cycle of existence. This is a bit more comforting a view than cold death, even if each cycle involves destruction by fire. What we learn from our current cosmological models is how fortunate we are to exist precisely when it is possible to exist. Of course, there is no luck involved here. We exist now because this is when it is possible for matter to agglomerate into thinking blobs like us. In other eras, there would be no stars capable of sustaining life long enough for it to conjecture about its fate. So if time will end, it is because creatures like us will also end. In a universe without sentient beings, aware of time's passage, without the awareness of past and future, the very concept of existence is meaningless. That should give us pause when we consider how small we are in the vastness of space. Small, yes, but as far as we know, we are the ones who hold the whole cosmic history in our minds. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
On the morning of July the 11th, 2022, the National Aeronautics and Space Administration, or NASA as we know it to be, unveiled the first images captured by the James Webb Space Telescope, or again, JWST, an instrument hailed as the most powerful space telescope in history. Named after NASA's second director, the telescope underwent a 26-year development process. The patience, time, and resources invested by the scientists at NASA into the JWST have been rewarded by the cosmos. The images of distant galaxies captured by the James Webb Telescope are gradually revealing information that challenges our understanding of the universe. Could we become the Galileos of this new era? Join us today as we watch this fascinating video, and welcome to Eyes 200M, where we will embark on a journey to explore the mysteries of the universe from the dawn of time. James Webb has discovered 700 galaxies beyond the edge of the Big Bang. The first achievement announced by the James Webb Telescope is the image capturing light from the SMACS 0723 galaxy cluster. This galaxy cluster is located at a distance of 5.12 billion light-years and lies in the southern part of the constellation Pisces. It is a patch of sky visible from the southern hemisphere of Earth and is often visited by the Hubble and other telescopes in search of deep cosmic history. The initial data is of immense significance, as it reveals the structure of the universe when it was just 600 million years old, measuring from the starting point of the Big Bang. Scientists anticipate that the JWST can uncover even more about the formation or demise of stars and planets, the shape of black holes, or the existence of extraterrestrial life. The latest information has somewhat fulfilled humanity's aspirations, as the images of 700 galaxies at the edge of the universe are sent back from James Webb. The evidence captured by infrared light has caused the scientific community to pause and reassess the models of the early universe. Can humanity overcome the shock of this knowledge and construct a new cosmological model based upon these new unimaginable discoveries? That remains an unanswered question. However, we all know that, quote, "Today the ancient hidden part of the universe will reveal itself, and our understanding of the cosmos will forever be changed," said Kenneth Sembach, director of the Space Telescope Science Institute, or TSTSI. So what exactly has the JWST unveiled about the universe? It is precisely the information that humanity has been searching for ages: the genesis of the endless cosmic night with its stars. Among the 700 galaxies within the reach of JWST's observations, astronomers have discovered 6 candidates that could overturn the entire theory of cosmic formation. The entire knowledge that we have built up until now may now be flawed, as the images from JWST reveal galaxies approximately 13.5 billion years old, containing tens of hundreds of billions of stars with masses equivalent to that of the Sun, just 500 to 700 million years after the Big Bang. This means that they are comparable in size to our own Milky Way galaxy. According to a recent study published on February the 22nd in the journal Nature, the newly discovered galaxies are so large that they contradict 99% of the representative models for early galaxies in the universe. This has left scientists utterly perplexed. The current theory suggests that galaxies begin their formation from small stellar dust clouds and gradually grow over time, but new discoveries are proving the opposite. It is, quote, reversing what many believed were well-established scientific theories, Joel Leja, an assistant professor of astronomy and astrophysics at Penn State University and co-author of the research paper, stated. These findings make the entire picture of the galaxy formation as we understand it uncertain. These 6 galaxies are not the oldest ones observed by JWST. Last year, scientists discovered 4 galaxies dating back to approximately 350 million years after the Big Bang, but those galaxies were much smaller in size. Dr. Emma Chapman, an astrophysicist at the University of Nottingham, who was not involved in the latest research, stated that further observations of other discoveries are needed before dismissing the current models of our universe. Currently, the research team is planning to gather spectroscopic images from the data sent back by JWST. This method can provide more accurate information about the age and allow for better estimates of the masses of the 6 new galaxies found. If you're interested in the latest results, please give us a like, subscribe, and turn on the notifications. EYES 200M will keep you updated and analyze the latest information for you. Now, let's delve into the hypothesis derived from the JWST discoveries. Will our understanding of star and galaxy formation change? Well, until now, the process of star and galaxy formation has remained shrouded in mystery. Erica Nelson, an astronomer at the University of Colorado Boulder, states, "Each year the Milky Way produces 1 to 2 new stars. In contrast, some of the 700 objects observed by JWST may generate hundreds of new stars annually and span throughout the history of the universe. If these findings can be verified, we will take a significant step forward in exploring and redefining the universe." End quote. We cannot rule out the possibility that these galaxies could be quasars or supermassive black holes. The new infrared images obtained by JWST will need further clarification on this matter. According to the theory describing the processes following the Big Bang, approximately 1 to 300 million years after the explosion, the first stars began to form. These were very large, bright stars responsible for the ionization process of the universe. At this time, we did not have yet elements heavier than lithium from the nucleosynthesis stage of the Big Bang. The first stars produced heavier elements through stellar nucleosynthesis. Therefore, the majority of the primordial light in the universe may be ultraviolet radiation from these very hot stars. The surface temperature of the stars also began to ionize hydrogen and neutralize helium around the stars after their formation. We refer to this event as the era of reionization. Scientists from the California Institute of Technology and the Sloan Digital Sky Survey have also found evidence for the final stage of this reionization process. They discovered strong absorption of ultraviolet radiation in the spectra of quasars at around 900 million years after the Big Bang. These findings suggest that the remaining neutral hydrogen was ionized at that time. If the stars were indeed very massive, their lifetimes would be very short, only a few million years. Some stars would explode in supernova, releasing the metals they produced. Stars with masses between 100 and 250 times that of the Sun are predicted to be completely destroyed in a powerful explosion. Most of the first stars fall within this mass range. Metals are more efficient than hydrogen in cooling the star-forming clouds and enabling them to collapse into stars. And even a small amount of metal production and release can have a significant impact on star formation. So, what is the contradiction here? If everything happened according to our previous understanding, the reionization process would occur more than 1 billion years after the Big Bang. After that, more stable stars would be formed. It would take billions of years more for galaxies to begin to appear. But now we have mature galaxies with ages as young as 500 to 700 million years old. What has happened to the theory of dark energy and the rate of cosmic expansion? Or are there still other mystery factors about matter and energy that we are yet to discover? Evidence of organic molecules in the early universe. Now, let us revisit the theory of the particle formation process to gather more evidence on how stars and galaxies were formed. According to a study published in the journal Nature in June of 2023, scientists using the JWST have discovered a cloud consisting of complex organic molecules within the galaxy SPT 0418-47, located 12.3 billion light-years away from Earth, and these are the oldest known organic molecules ever identified by humans. The spectroscopic data reveals that these organic molecules belong to complex forms, primarily aromatic polycyclic hydrocarbons, or PAHs for short. On Earth, PAHs are found in forest fire smoke and car exhaust fumes. In space, they may play a significant role in star formation. Scientists speculate that they help regulate the temperature of gas clouds in stellar nurseries, thereby influencing the timing and location of star development. PAHs are considered one of the fundamental building blocks for the longest-lasting forms of life here on Earth. What does this mean? Isn't it fascinating that these organic molecules existed in the early universe just over 1 billion years after the Big Bang? This is something that no cosmological model has ever addressed. Joaquin Vieira, a co-author of the study from the University of Illinois Urbana-Champaign in U.S., stated, quote, "We were very surprised by this discovery. It has provided new insights into the complex chemical interactions occurring in the early galaxies of the primordial universe. The detection of these complex organic molecules at such a distance is a significant breakthrough," end quote. Humanity first became aware of the galaxy SPT 0418-47 in 2020 using the South Pole Telescope of the National Science Foundation. The mass of the stars could only be determined through a physical trick called gravitational lensing. This effect occurs when light from a distant object is curved around a nearby massive object due to its gravitational force. During this process, the distant light is distorted and magnified, and in the case of SPT 0418-47, scientists calculated that it appeared over 30 times brighter. During the analysis of this light, initial findings indicate that SPT 0418-48 contained a significant amount of heavy elements. However, the South Pole Telescope was unable to provide a clear view of its carbon-containing organic components due to inadequate wavelengths. Thanks to the JWST, though, everything is much clearer now. Justin Spilker, an astronomer at Texas A&M University and the lead author of the study, stated, quote, "Everywhere we look, we see molecules associated with forming stars. This supports the hypothesis that organic molecules aid in the birth of stars," end quote. However, what remains puzzling is the uneven distribution of PAH cloud densities. This still remains an unanswered mystery for us all. SPT 0418-47 exhibits several similarities to our own Milky Way galaxy, which is unusual for an ancient galaxy. Galaxies from the early universe are typically thought to have different shapes compared to those observed today. Francesca Rizzo, a researcher at the Max Planck University for Astrophysics in Germany, stated, "This discovery represents a breakthrough in the study of galaxy formation, revealing that the structures we observe in nearby spiral galaxies and in our Milky Way even existed 12 billion years ago," end quote. I cannot express enough how remarkable this finding is. We can utilize these studies to determine the time frame in which the universe and galaxies formed. It is possible that in a distant place, billions of light years away, a civilization similar to Earth was formed and continues to exist today. This is truly awe-inspiring. Conflicts regarding the formation of galaxies. According to our current theories, there are two ways in which galaxies form. The first model asserts that giant elliptical galaxies are formed through the rapid collapse of dark gas and matter. During this process, most of the dust clouds quickly transform into stars. Subsequently, galaxies only undergo slow changes as stars evolve. This scenario is referred to by astronomers as the top-down process. The second model demonstrates that giant elliptical galaxies are primarily formed through the merging of smaller galaxies. They undergo a transformation of their gas content as stars form, following a bottom-up scenario. These observations, when considered together, suggest that the giant elliptical galaxies we observe today are formed through a combination of both top-down and bottom-up mechanisms. In the case of the largest galaxies, formed within the densest matter clusters, both processes occurred early and rapidly in cosmic history. However, both hypotheses for galaxy formation assume that they occurred billions of years after the Big Bang. At that time, the universe was at least 9.8 billion years old, with dark energy causing the expansion rate to be slower and more stable. If the evidence for the earliest galaxies from the James Webb telescope is accurate, we will have to reconsider our models. It is possible that we will develop new theories about dark matter. But what is evident here is that the expansion rate of the universe could be significantly higher than the speed of light. Despite significant efforts, humanity still does not fully understand the majority of the knowledge related to dark matter and dark energy. This is the greatest variable that affects cosmic research and exploration. To address this issue, NASA and the U.S. Department of Energy plan to establish the Joint Dark Energy Mission, or JDEM, the first program created to study dark energy. However, the JDEM project did not receive funding, which is extremely regrettable. Why and how does dark energy relate to the formation of galaxies? This is a long and complex story. However, if you're interested, please follow and comment and let us know. In addition to providing the latest information from scientific journals, we are also delighted to assist you in exploring other interesting and fascinating areas of astronomy. Thank you for watching this episode today. We look forward to seeing you again in upcoming issues.
Out in the depths of space, the James Webb Space Telescope is already revolutionizing what we thought about the universe. For James Webb, the hits just keep coming, one riveting image after another, from the far reaches of the universe to planets right here in our own solar system. We got our first taste a year ago, and the images did not disappoint. The Carina Nebula, Stephan's Quintet, and, spectacularly, this so-called deep field image showing thousands of galaxies stretching into the distant universe. But perhaps the most amazing thing revealed by James Webb is that the furthest you look back in time, there were already huge, mature, and fully formed galaxies that shouldn't exist. Some of them even might be older than the universe, and scientists call them universe breakers. Nobody expected them. They were not supposed to be there. And now, nobody can explain how they had formed. So, is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb's shocking discoveries could shatter our leading explanation for how the universe began. Originally, the Big Bang was a simple idea that grew out of three facts, all put together. In Einstein's general theory of relativity, a universe filled with any uniform distribution of matter and/or energy will not be stable in a static configuration. The fabric of space in that universe must either contract or expand. Observationally, there are spirals and ellipticals in the sky, and they lie well beyond the Milky Way. Their distances can be measured. Also observationally, the light from these spirals and ellipticals appears to be shifted, with more distant objects exhibiting a greater redshift in direct proportion to their distance, consistent with an expanding universe. By combining these three facts, we'd conclude that the universe, if it's expanding and becoming less dense today, must have been smaller and denser in the past. We can extrapolate this back farther and farther, to even very early times if we like, and recognize that our modern universe must have emerged from a denser, smaller, more uniform state in the very distant past. The first person to synthesize this information together was Georges Lemaitre, who did it in 1927, although others would independently come to the same conclusion, including Howard Robertson in 1928, Edwin Hubble in 1929, and Arthur Walker a few years later. Over time, we were able to derive many more consequences from the Big Bang, including that the early state must have been hotter as well as denser, and that as the universe expands, it also cools. This allowed us to predict that there would be a leftover bath of low-energy radiation with a blackbody spectrum in all directions arising from when the universe cooled through the threshold that enabled it to form neutral atoms. That the universe would have, at even earlier times, been hot and dense enough to initiate nuclear fusion reactions before any stars could form, leaving us with an initial abundance of elements other than hydrogen among the pristine set of atoms that the universe begins with. And that, once neutral atoms form, the universe begins gravitating to form structure in the universe. Stars, star clusters, clouds of gas, galaxies, galaxy clusters, and eventually the great cosmic web, filled with filaments and voids. All of these aspects of the Big Bang have been verified and validated, ruling out a great many alternatives that cannot reproduce these successes. Today, there are 3 additional ingredients that we've learned, and tested and verified, are also present in the universe. Dark matter, which clumps and gravitates but doesn't collide with normal matter or photons. Dark energy, which behaves as a form of energy inherent to space itself. And cosmic inflation, which limits how far back into the past we can extrapolate the hot Big Bang before matter and radiation no longer dominated the energy contents of the universe. This picture enables us to do something remarkable. Inflation allows us to describe the initial conditions of the universe at the start of the hot Big Bang. How hot and dense it was, what the initial spectrum of density imperfections were, including that were all adiabatic Gaussian random fluctuations, and what the magnitude of these fluctuations were on all cosmic scales. Our knowledge of the Standard Model, plus the additions of dark matter and dark energy, enable us to state what the various types, energies, and abundances of all the different species of energy were at all cosmic times. From that starting point, our knowledge of the laws and interactions that govern the universe enables us to time evolve these initial conditions from the start of the hot Big Bang all the way up through the present day. We can make both theoretical predictions and perform numerical simulations that tell us what should arise and when, in an expanding universe that begins with a hot Big Bang and the properties we've determined it ought to have. However, despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. And with the recent addition of the James Webb Space Telescope to the arsenal of tools astronomers have, James Webb continue fuel doubts about the Big Bang theory, as its early universe observations cannot be explained by current cosmological models. The James Webb has literally gone further than any similar instruments used by NASA before. As Matt Greenhouse, who has served on the James Webb's senior staff as a project scientist, the James Webb Space Telescope has given humanity its first high-definition view of the infrared universe. Thanks to Webb's unprecedented capabilities, for the first time, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Prior to James Webb, we had one confirmed galaxy GNZ11 at an age of about 400 million years after the Big Bang, and only one other galaxy candidate, possibly at an age of around 330 million years after the Big Bang. No other stellar or galactic signals from such early epochs had ever been seen. Fast forward to the present day, more than 1 year after James Webb began science operations, and the story has changed dramatically. We have over 100 galaxy candidates from James Webb that take us back to the first 400 million years of the universe, and several of them have already been confirmed to indeed be ultra-early and ultra-distant. GNZ11 already is now only the 5th most distant galaxy known, and it's fully expected that over the next months, not only will the current cosmic record for distance, jot as GSZ13-0, from a time just 320 million years after the Big Bang, be broken, but that at least dozens of new ultra-early, ultra-distant galaxies will soon be confirmed. Many of these early galaxies that James Webb is finding have peculiar, puzzling properties about them that appear difficult to reconcile with this theoretical picture that the universe has painted for us. For example, they appear to be very massive, very bright, very rich in heavy elements, very actively forming new stars, and very rich in gas. The fact that we see so many galaxies with these properties so early on is puzzling, because we believe we understand how gas infalls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long timescales. Therefore, when we look at these very early galaxies, we do get the impression that something is amiss. It is clear that galaxies captured by James Webb are so massive that they should not be possible under current cosmological theory. Thus, Big Bang astronomers are now stunned and surprised because, according to the Big Bang theory, those galaxies shouldn't be there. There should have been only primordial dust from which they assume that stars and galaxies originated after a primeval explosion. The James Webb Telescope is challenging the Big Bang theory held by most scientists, and it is causing consternation in the scientific community, at least among those scientists who believe in the Big Bang origin of the universe. Big Bang scientists believe that the expansion of galaxies in the universe came from a singularity that exploded billions of years ago. Yes, some galaxies may be expanding, moving further away, what is called red shift. But this is not necessarily the case with the entire universe, and not even all scientists, including evolutionary scientists, interpret red shift in our universe as meaning galaxies are expanding, or that there was a primeval Big Bang from which the universe sprung. It has been said that publishers of prestigious science journals refuse to publish papers and research from scientists who refute the Big Bang theory. Canadian physicist and scientist David Rowland asserts in his internet article, "The Big Bang never happened," several scientific contradictions to the Big Bang that have been conveniently glossed over or ignored in order to support the much-cherished Big Bang theory held by the majority of scientists. These scientists have had to resort to the internet to publish their scientific arguments refuting the Big Bang theory. Rowland says that the red shift in actuality is not a measurement of velocity, of showing that galaxies are expanding and moving away, but only a measurement of temperature and distance. He says that Big Bang scientists initially confused the red shift from galaxies with the Doppler effect, and this confusion led these earlier scientists to believe that the universe was expanding. Rowland points out that the light from galaxies naturally attenuates over long distances, and that this attenuation had been wrongly interpreted by early scientists as evidence that galaxies in our universe must be expanding. Once this belief had set in early on, it continued to be taught and held by the majority of scientists to this day. Even the famed astronomer Edwin Hubble, after whom NASA named its famed telescope, and who discovered the redshift, expressed doubts about interpreting the redshift as evidence that galaxies are expanding. Hubble believed there could be other reasons for the redshift. Hubble refused to believe that the redshift was proof of galaxies expanding. Even if there was a past expansion of galaxies, this does not mean that the galaxies at present are expanding. We can only see the past from telescopes, not the present. Interestingly, the Bible teaches that the heavens at one time expanded. Various passages in the Bible speak of God stretching out the heavens. If the Big Bang really occurred, there would have been a uniform distribution of gases in space. This uniform distribution of gases throughout the universe would have made sure that the gases didn't have enough gravitational attraction to form into planets and stars. Big Bang scientists must assume the existence of dark matter in the universe to provide enough gravitational force for stars and galaxies to form. However, there still is no scientific proof for the existence of dark matter. In fact, the hypothesis of the existence of dark matter has been increasingly discredited by science. Big Bang scientists believe that dark matter can be the only gravitational explanation for how galaxies behave. However, other scientists have successfully shown an alternative explanation to dark matter known as MOND, which stands for Modified Newtonian Dynamics. In other words, It is not necessary to believe that 80% of the universe must be made up of dark matter in order to explain certain behavior and movement of galaxies. The late creationist and scientist Dr. Duane T. Gish said, "The galactic structures discovered during the past few years, however, are so massive that even if cold dark matter did exist, it could not account for their formation." Furthermore, an explosion cannot explain the precise and orderly orbits and courses of thousands of billions of stars in thousands of billions of galaxies. Gravity may explain how that order is maintained, but mere gravity cannot explain the origin of that order. The disorder in the universe can be explained because of chance and random processes, but the order can only be rationally explained because of an intelligent power. Some evolutionary astronomers believe that trillions of stars crashed into each other, leaving surviving stars to find precise, orderly orbits in space. Not only is this irrational, but if there was such a mass collision of stars, then there would be a supermass residue of gas clouds in space to support this hypothesis. The present level of residue of gas clouds and dust in space doesn't support the magnitude of star deaths required for such a hypothesis. It's more rational to believe that stars die and decay into gas clouds and dust instead of believing that gas clouds and dust evolve into stars, as evolutionary astronomers teach. Evolutionary astronomers only assume that gas clouds and dust in the so-called pillars of creation are birthplaces for stars. This assumption is conveniently passed on as fact in textbooks and media. In another remarkable effort to explain Webb observations, the scientist proposed a hybrid model that combines aspects of the tired light model and a cosmological model based on evolving coupling constants. This new model suggests a longer galaxy formation time, allowing for the formation of well-evolved early galaxies. However, further research and scrutiny are required to determine if this model can provide a satisfactory explanation for all the observations in cosmology. On the other hand, the need for a new cosmology is not unprecedented in the scientific community. Mixing models to explain new observations has been done in the past, such as Albert Einstein's explanation of the particle-like and wave-like nature of light. Similarly, estimating the age of the universe based on the age of stars in globular clusters has also been used as an alternative method. In conclusion, the discrepancies between observations and the standard model of cosmology have prompted the proposal of a new model that suggests a longer age for the universe. While this new model shows promise, further research is needed to determine its validity and if it can provide a comprehensive explanation for all cosmological observations. And as a worth note, the eagle eye of James Webb has just discovered two of the most distant galaxies ever seen, supporting the basic picture of galaxy formation as described by the Big Bang theory. The discovery was made possible thanks to a huge helping hand from a massive gravitational lens in the form of the galaxy cluster known as Abell 2744, nicknamed Pandora's Cluster, which is located about 3.5 billion light-years away from us. The immense gravity of the cluster warps the very fabric of space-time sufficiently to magnify the light of more far-away galaxies. Using the James Webb Space Telescope to search for early galaxies magnified by this cosmic lens, Bingji Wang of the Penn State Eberly College of Science and member of the James Webb Space Telescope Ultra-Deep Near-Infrared Spectrometer and Near-Infrared Camera observations before the epoch of Ryanization or Uncover team discovered two of the highest redshift galaxies ever seen. Cosmological redshift, as told, is the stretching of light wavelengths, provoked by the continuous expansion of the universe. The more distant a galaxy is, the more the universe had expanded while that galaxy's light traveled across space to reach us, and therefore, the more the wavelengths of that light are stretched. As wavelengths get stretched out in this manner, they go from tighter, bluish ones to redder ones, eventually falling into the invisible infrared region of the electromagnetic spectrum. Galaxies that existed just between 300 and 400 million years after the Big Bang have had their light stretched into those infrared wavelengths that can't be seen by humans, but can indeed be detected by the Webb's near-infrared camera and near-infrared spectrometer instruments. Wang and her team were able to identify the lensed images of two high redshift galaxies. One, designated Uncover Z13, Z is shorthand for redshift, has a redshift of 13.079, confirming it to be the second most distant galaxy known. The most distant confirmed galaxy is Jade's GSZ 13.0, which was also discovered by the James Webb in 2022 and has a redshift of 13.2. We see Uncover Z13 as it existed just 330 million years after the Big Bang. The other galaxy recently discovered, Uncover Z12, has a redshift of 12,393, placing it in fourth place in the all-time list of most distant galaxies. We see this realm as it was just 350 million years after the Big Bang. What marks the two Uncover galaxies out as different is their appearance. Other galaxies seen at similarly high redshifts seem to be point-like, indicating they are very small, just a few hundreds of light-years across. The Uncover galaxies, on the other hand, have structure. Previously discovered galaxies at these distances appear as a dot in our images, Wang said in a statement, but one of ours appears elongated, almost like a peanut, and the other looks like a fluffy ball. These galaxies are also bigger, with Uncover Z12 sporting an edge-on disk about 2,000 light-years across, which is 6 times larger than other galaxies seen in this era. It is unclear if the difference in size is due to how the stars formed or what happened to them after they formed, but the diversity in the galaxy properties is really interesting, said Wang. These early galaxies are expected to have formed out of similar materials, but already they are showing signs of being very different than one another. Although the dichotomy in galaxy properties, even at this early stage in the universe, is eye-opening, both of the newfound realms have general characteristics that are strongly supportive of the Big Bang model. This model describes how, in the aftermath of our universe's creation, galaxies began life small before growing rapidly through mergers with other galaxies and gas clouds. This growth, in turn, spurred more star formation, which ultimately increased the abundance and variety of elements contained within the young galaxies, introducing substances to them that are heavier than hydrogen and helium. The galaxies uncovered by Uncover, if you'll pardon the pun, are young, small, have a low abundance of heavy elements, and are actively forming stars, all of which supports the whole paradigm of the Big Bang theory, Joel Leja, who is an assistant professor of astronomy and astrophysics at Penn State University and a co-researcher on Wang's team, said in the statement. Interestingly, the Webb telescope has the ability to see even higher redshift galaxies than Uncover Z13 and S12, meaning they'd be even younger, but it didn't detect any being lensed by the Pandora cluster. As Leja said, that could mean that galaxies just didn't form before that time and that we're not going to find anything farther away. Or it could mean we didn't get lucky enough with our small window. Astronomers will keep looking, using a multitude of lensing clusters to open up new windows into the deep universe in search of some of the first galaxies. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
Something is awry in our expanding cosmos. Nearly a century ago, the astronomer Edwin Hubble discovered the balloon-like inflation of the universe and the accelerating rush of all galaxies away from each other. Following that expansion backward in time led to our current best understanding of how everything began: the Big Bang. But over the past decade, an alarming hole has been growing in this picture. Depending on where astronomers look, the rate of the universe's expansion a value called the Hubble constant, varies significantly. Now, more than 2 years after its launch, the James Webb Space Telescope has cemented the discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. According to Adam Rees, a professor of astronomy at Johns Hopkins University, who led the team that made the new James Webb measurements, it's a disagreement that has to make us wonder if we really do understand the composition of the universe and the physics of the universe. On this, many cosmologists can agree. It started with a bang. Then, in an instant, the young cosmos was formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence, only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma mire should have consumed each other entirely. But scientists believe that some unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high energy density of the early universe's crowded contents stretched space-time, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, the standard story goes, ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies, connected together by a vast cosmic web. Initially, as the universe's content spread out, its energy density and therefore its expansion rate decreased. But then, roughly 5 billion years ago, galaxies began to recede once more at an ever faster rate. The cause was another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the stretching fabric of space-time. Einstein named it lambda in his theory of general relativity. As our cosmos grew, its overall matter density dropped, while the dark energy density remained the same, gradually making the latter the biggest contributor to its overall expansion. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. They are also key ingredients in the lambda cold dark matter or LCDM model of cosmology, which maps the growth of the cosmos and predicts its end. With matter eventually spread so thin, it experiences a heat death called the Big Freeze. Many of the model's predictions have been proven to be highly accurate, but here's where the problems begin. Despite much searching, astronomers have no clue what dark matter or dark energy are. As Ofer Lahav, a professor of astronomy at University College London who is involved in galaxy surveys of dark energy, said, "Most people agree that the universe's present composition is 5% ordinary, atomic matter, 25% cold, dark matter, and 70% dark energy. The embarrassing fact is, we don't understand the last two of them. But an even greater threat to the LCDM model has materialized. Depending on what method astrophysicists use, the universe appears to be growing at different rates, a disparity known as the Hubble tension. And methods that peer into the early universe show it expanding significantly faster than LCDM predicts. Those methods have been vetted and verified by countless observations. Therefore, as Rees said, the only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion takes a little bit more than a radar gun. The first method to measure this growth looks at the so-called cosmic microwave background, or CMB. a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump. As the universe exploded outward, this soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant, or dark energy. Plugging these into the standard model spat out a Hubble constant of roughly 67 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. Let's pause on this number for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will retreat from us, and us from it, at 67 kilometers per second. At 20 megaparsecs, this recession grows to 1,340 kilometers per second, and continues to grow exponentially there onward. If a galaxy is any further than 4,475 megaparsecs away, it will recede from us faster than the speed of light. A second method to find this expansion rate uses pulsating stars called Cepheid variables, dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, making them periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt found that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness, and therefore gauge its distance. It was a landmark discovery that transformed Cepheids into abundant, standard candles to measure the universe's immense scale. By stringing observations of pulsating Cepheids together, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate means that astronomers have today for measuring distances. Wendy Friedman, an astrophysicist at the University of Chicago, said, "To build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 kilometers per second per megaparsec when compared to the Planck measurement. Yet Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So, when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meter wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 meter wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC4 258 with bright Type 1, a supernova's, another standard candle because they all burst at the same absolute luminosity, in remote galaxies, Rees and his colleagues arrived at a nearly identical result: 73 kilometers per second per megaparsec, including one made by Friedman, with the Hubble Space Telescope on the rapid brightening of the most luminous tip of the branch, red giant stars, and another with light bent by the gravity of massive galaxies, came back with respective results of 69.6 and 66.6 kilometers per second per megaparsec. A separate result using the bending of light also gave a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling. According to Ryan Keeley, a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension, the CMB temperature is measured at the level of 1% precision, and the Cepheid distance ladder measurement is getting close to 1%. So a difference of 7 kilometers per second, even though it's not very much, is very, very unlikely to be a random chance. There is something definite to explain. The new result leaves the answer wide open, splitting cosmologists into factions chasing staggeringly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, or KITP, in California, only caused more frustration. As David Gross, former director of the KIT and a Nobel laureate, said at the conference, "We wouldn't call it a tension or problem, but rather a crisis." But how things can be fixed is unclear. Rees is pursuing a tweak to the LCDM model that assumes dark energy isn't constant, but instead evolves across the life of the cosmos, according to unknown physics. However, Keeley's research contradicts this. He and his colleagues found that the expansion rates matched the predictions of LCDM model all the way back to the CMB. So, if the model needs fixing anywhere, it's most likely in the very early universe. It could be possible to add some extra dark energy before the emergence of the CMB, giving some additional oomph to the universe's expansion that needn't make it break from the standard model. Another group of astronomers is convinced that the tension alongside the observation that the Milky Way resides inside an underdense supervoid means that LCDM and dark matter must be thrown out altogether. What should replace it, according to Pavel Krupa, a professor of astrophysics at the University of Bonn, is a theory called modified Newtonian dynamics, or MOND for short. The theory proposes that for gravitational pulls 10 trillion times smaller than those felt on Earth's surface, such as the tugs felt between distant galaxies, Newton's laws break down and must be replaced by other equations. Other astronomers say that their own calculations nix the MOND claims, yet Krupa insists that cosmologists looking to tweak the standard cosmological model are basically adding additional complications to an already very messy and complicated theory. According to Krupa, what we are experiencing and witnessing is an essential breakdown of science. A more optimistic thought, it's possible that the standard model just needs a tweak, or maybe dark matter and dark energy are the modern-day equivalent of epicycles, the small circles ancient Greek astronomers used to model planets orbiting Earth. The orbits of planets were described very accurately by epicycles, Lahav said. It was a good model. It fitted the data. But once astronomers placed the sun in the center of the solar system in newer models, epicycles eventually became irrelevant. If we want to go philosophical, maybe that's what's going on. But maybe also there is dark matter and dark energy, and it's just not been discovered yet. Cosmologists are looking for answers in a number of places. CMB experiments, such as the CMB S4 project at the South Pole and the Simons Observatory in Chile, are searching for clues in ultra-precise measurements of the early universe's radiation. Others will look to the dark matter maps produced by European Space Agency's Euclid Space Telescope, or to the future dark energy survey conducted by the Dark Energy Spectroscopic Instrument. Although it now may seem less likely, it's also still possible the Hubble tension could be resolved by figuring out some unseen systematic flaw hiding inside current measurements. And for scientists like Friedman, such a solution, or possibly further riddles, will come from James Webb. Her team is using the telescope's powerful eye to make ultra-detailed measurements of Cepheid variables, tip of the red giant branch stars, and a type of carbon star called JAG-B stars all at once distance. Once the necessary data is collected, we'll see how well they agree, and that will give us a sense of an overall systematic answer. In other words, one day, the James Webb Telescope could settle a long-standing debate. Just hope that day comes soon. After all, as you see, while it would seem that scientists and astronomers know an awful lot about the universe, we are nowhere near knowing everything there is to know. There are still many unsolved mysteries surrounding our universe. Here are some of the most pressing issues occupying the finest astronomical minds of the 21st century, and they expect James Webb to shed light on the mysteries of our vast universe. How supermassive black holes merge. When a black hole smashes into another black hole, it sends shock waves rippling out through space itself, gravitational waves. Yet so far, the mergers we've seen have come from so-called stellar mass black holes, those with masses a few tens of times the mass of our sun. That's tiny compared to a supermassive black hole, which can tip the scales at billions of solar masses. There's a supermassive black hole in the center of every major galaxy, and galaxies also collide. So what happens to the two black holes at their hearts? You'd think that they'd merge too, but there's a problem. To spiral inwards, the black holes need to lose energy, which they do by shedding heat to surrounding gas, dust, and stars. Yet when they get within a parsec of each other, there's no longer enough stuff to lose energy to. This final parsec problem means the supermassive black holes should remain orbiting each other and never actually merge. However, recent evidence from the nanograv experiment suggests that the universe is humming with gravitational waves from supermassive black hole mergers. The data from this hum might give astronomers the clues they need to finally unpick this problem. 2. What the universe actually looks like. Look at the large-scale structure of the universe today, and countless galaxies are strung out on endless filaments in a cosmic web. It seems that tiny variations in density in the very early universe acted as seeds from which this structure eventually blossomed. Over dense regions drew in more and more material to create galaxy-filled superclusters and leave behind supervoids. Except the Big Bang Theory says that the early universe should have been completely smooth. How come it had tiny imperfections of just a few parts in 100,000, but which created the universe as we see it today? One explanation is a modification to the Big Bang called inflation, which states what happened in the first few seconds of the universe. It argues that the universe underwent a period of super rapid expansion in the first minuscule fraction of a second. The cosmos went from considerably smaller than an atom to about the size of a grapefruit in a trillionth of a trillionth of a trillionth of a second. Before this, the universe was so small that it was dominated by minute quantum variations. The ensuing explosion in size blew up those variations. It's worth saying that currently there's no evidence that inflation really happened, although it does help solve other problems with the Big Bang too. Nor do we know the universe's true size. Astronomers speak about the observable universe, a spherical region 13.8 billion light-years in all directions where light has had time to reach us since the Big Bang. However, there could well be things beyond this cosmic horizon that are so far away the light hasn't arrived at Earth yet. This also makes it difficult to determine what shape the universe is. Astronomers currently believe the 4D fabric of space-time is flat, but it could simply be that inflation has smoothed out the billions of light-years we can see. And beyond that, the universe is actually curved. One thing we don't know about the universe is its shape. 3. What gravity really is. While we know what gravity does, it's unclear how it does it. Our current best theory of gravity is Einstein's general theory of relativity. It says that massive objects like the sun warp space-time, the fabric of the universe, around them. Earth is then caught in the distortion that the sun makes, which is why we orbit. Except this isn't how physicists treat any of the three other fundamental forces. They are all carried by particles called bosons. Magnets attract each other, for example, by exchanging bosons called photons. So the hunt is on for the graviton, a so far hypothetical particle that would be responsible for gravity. 4. What happens inside a black hole? One of the most asked questions about black holes is, what would happen if you fell into a black hole? Wander too close to the horizon of a black hole, and the extreme difference in gravity between your head and your feet would rip you apart into lengths of human spaghetti. But where does that pasta eventually end up? Our best theory of black holes is Einstein's general theory of relativity. It says that inside a black hole space becomes increasingly concentrated into an ever smaller volume. In fact, at the very bottom space is crushed into an infinitely small speck called a singularity. However, a singularity is likely to be a placeholder for our ignorance. The curvature of space becomes infinite, and the singularity's density becomes undefined. In other words, the laws of physics suddenly lose their predictive powers. The elephant in the room is quantum physics. If you squeeze space down into a volume smaller than an atom, then quantum physics probably has something to say on what happens. However, despite many valiant attempts, physicists have yet to combine general relativity and quantum physics in a satisfactory way. If we one day create a so-called theory of everything, we may find out what we need to replace a singularity with. 5. What dark matter is. There's something about galaxies that just doesn't make sense. They're rotating far too fast. So fast that their outer stars should fly off into space, but that's not happening. Instead, astronomers suspect that galaxies contain an invisible gravitational glue called dark matter that helps to keep hold of those stars. But what is dark matter made of? This is one of the most significant things we don't know about the universe, in that it's a key unanswered question. For decades, the leading idea has been something called weakly interacting massive particles, or WIMPs. Except physicists have gone to great lengths and performed extensive and exhaustive searches for them, and they haven't seen a single one. And so they're starting to look seriously at other options. Other candidates include that dark matter is caused by the gravity of tiny black holes formed shortly after the Big Bang, known as primordial black holes. Or dark matter could be particles called axions, which physicists conjured up to solve a problem in particle physics. There's a chance that dark matter isn't actually a physical substance at all, but an illusion instead. This is the premise behind a theory known as MOND. It says that the missing gravity is actually due to the fact that gravity works differently on the scale of galaxies, and we've been misinterpreting the situation. 6. Which way up galaxies form. There are hundreds of billions, perhaps even trillions, of galaxies in the modern universe. But where did all these star cities come from? There appear to be two ways to make a galaxy. You could start small with individual stars and minor star clusters. Over time, gravity, added by the glue of dark matter, could then bind lots of these together to form the conglomerations we call galaxies. This is a so-called bottom-up approach. The alternative is top-down, where huge structures form early in the universe's history, only to fragment into galaxies as the cosmos aged. The James Webb Space Telescope is currently wowing astronomers with insights into the early universe. It has seen fully fledged galaxies just 400 million years after the Big Bang, and even some that appear to be merging. So that seems to favor the bottom-up approach, but it needn't be a binary situation. It may be possible for some galaxies to form bottom-up, while others formed top-down. Huge upcoming galaxy surveys like those with the Vera Rubin Observatory in Chile could help us to know more. Plus, the Webb telescope is only just getting started. 7. How the universe will end. Astronomers used to think that the gravity of everything in the universe would eventually pull the cosmos back in on itself in a reversal of the Big Bang, dubbed the Big Crunch. However, that was before they discovered that the expansion of the universe is accelerating due to a shadowy entity known as dark energy. If it continues to accelerate, all structures in the universe, even atoms, will be torn apart within 22 billion years in a so-called Big Rip. A more sedate expansion would lead to a big freeze instead, where the expansion of the universe causes it to cool so much that stars cannot shine, and the universe eventually settles into a uniform temperature. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching,